that is lifestyle for environment topic, and under that also you've chosen such a wonderful topic about the resilient thinking for managing our resource constrained world. So it's such a wonderful topic to be talking about. So not taking much time, I welcome all the participants, all our faculty members, and sir especially, to talk about this topic. Thank you so much. Thank you so much, ma'am. It is my distinct pleasure to introduce our esteemed keynote speaker for today before inviting him to the podium. Dr. Ganti S. Murthy is a professor in the Biological and Ecological Engineering Department at Oregon State University. Dr. Murthy's research is broadly focused on sustainable bioprocessing. His group, Murthy Group, employs a combination of experimental and theoretical approaches using control theory, system biology, process modeling, economic analysis, and life cycle assessment techniques to conduct molecular, cellular, industrial scale and system level analysis of technologies to establish a sustainable bioeconomy. Recently, Murthy Group started researching the nutrient energy water nexus at regional and global scale with a particular focus on building the resilience of agroecological systems to pulse and pressure disturbances. We eagerly await your keynote address, sir, hoping to gain invaluable insights and guidance on the topic resilience thinking for managing our resource constant world. So may we please welcome Professor Ganti with a huge round of applause.
Very good evening to all of you. Glad to be here, and glad to be speaking to our engineers, young ones. And I was just before this talk, we had a discussion in the lounge there, and got to know that a lot of you are starting and as fresh going through the induction programs as fresh engineers who will be having a long, successful career. So cheers to that. And a lot of you are also mid-career professionals who are here for refresher programs. So again, namaste to all of you for that. And anyway, so we'll get into this topic. So I was thinking when Tripta asked me to come here and talk, one of the things I was thinking about was, what is it that as an engineer who has worked in a lot of the agroecological systems and a lot of these ecosystems, what would I talk and work on bioenergy and energy transition, these kind of things? What would I be talking to you guys that would be different from what you already know? What would be the fundamental things that we need to think about? So I was basically thinking about the problems that keep me up at the night and I'm very passionate about. That is about when we think about the challenges that we are facing today. So if you think about the kind of those of you who are here for the refresher courses, if you look back at what your undergraduate education was, maybe 20 years ago, 30 years ago, then the kind of curriculum that we had then and the kind of problems that were there, don't exist today. So similarly, the kind of problem that we are going to see around today will not be there 20 years or 30 years down the line. So what would be my message to young engineers who would come here so that we can solve not today's problems? Of course, we need to do that, but also be prepared with enough tools to solve problems that will come to you 20 years down the line when you are in different managerial positions and you are going to manage lot more people and systems across the country. So then this is something that I was thinking about, because this is a problem that you are going to increasingly be confronted with, and you will be asked to deal with this as we go forward. So essentially, it is about resilient thinking for a resource-constrained world. Basically, what is motivation for this talk? One of the things that I wanted to talk about was we live in a small world. I mean, remember that Carl Sagan, anybody remembers that Carl Sagan's pale blue dot? The Earth, picture from the Voyager. It was just essentially, when we looked, the Voyager looked back, spacecraft looked back at the solar system, then all we saw was a pale blue dot, less than 1 pixel. That was essentially the Earth. That is where we are living. And then we have human populations growing, and we are consuming resources at an increasing rate. And then we live in a world that is extremely complex too. We don't understand all parts of it. And engineering systems are complex enough. Natural systems are non-linearly more complex. And then how do you deal with such systems, and especially at the interface of these things? So that was essentially the motivation for my talk. And if you think about it, if you look at the economics, why am I going to talk about economics, politics, social sciences, and also the engineering? Because that is what we will be confronted with. It will engineers' problem. What is the difference between an engineer and a scientist? If you think about it, as engineers, we are expected to solve a problem. It is not enough for us to analyze. We have to analyze and come up with a solution. Unless our solution works, we cannot be good engineers. And so these are the kind of problems you will be faced with, and you need to deal with all of that in your career. So if you look at any complex problem, what happens is typically this: 6 blind men and the elephant type problem. Each of us will be looking at different parts of the system, and to get an understanding of a complex system, it's extremely difficult. And that leads to think about how do we come up to basically confront such problems, perhaps using some of the tools like systems thinking. But then you will be hearing a lot about sustainability, especially if you think about what is sustainability. I mean, this is essentially obviously core to our progress of the societies, and is a foundation for all the developmental goals. In fact, if you see UN's Sustainable Development Goals, these are the 17 sustainable goals, development goals that are out there. Since 2015 or so, everybody is talking about this. Corporate houses talk about it. All the government agencies talk about it. Think tanks talk about it. Everybody, UN, G20, everybody talks about these goals. So, and then when did this kind of sustainability come into lexicon of essentially all the discourse? If you think about it, started in 1987 when there was a UN Brundtland Commission's report where they defined sustainability as one of the things. And it has, again, long history. Back in 1972, there was something called a limits to growth that was published by Club of Rome. What they were basically saying was, if we grow at the rate at which the world was growing in 1972, we would run out of resources. Because ultimately we live on a resource-constrained planet. We don't have, we have a limited amount of energy sources, we have a limited amount of mineral sources, we have a limited amount of water sources and everything. So how do we manage that? So then essentially the whole this thing was about how do we have a development that is sustainable. And it was applied to policies, visions and declarations. And whenever you talk about any metric like sustainability, it is important to see what are the components of it. And then basically people started talking about sustainability is not just about environment, it is also about economics, it is also about societal aspects, right? Because then how do we say, for example, in India, our per capita electricity consumption is very low compared to what it is in US or Europe or some other place. In Africa, it is even lower in some of the African countries. How can we say that I want to reduce the CO2 emissions by shutting down all the coal power plants in our country if, without basically comparing all the historical emissions? Because that is also just that environmental justice also has to be there. All of these arguments are there. And so then people started realizing that this is not a so simple this thing. And then they came up with these goals and all that, but still, there is a lot of ambiguity here. So, but then the point is, we live in an era called Anthropocene. What is Anthropocene era? Essentially, we live in an era where activities of the human beings in the last 10,000 years have been so significant that they are influencing the planetary things. Essentially, planetary fluxes of nitrogen, planetary fluxes of water, energy flows. We are influencing all of these because of our activities. And then this brings to the question, does this mean that this is the end of sustainability concept? Do we say that because Anthropocene is leading to irreversible changes and limitations, does this mean we have to think about sustainability in a different way, or is it the end of sustainability? There was actually a paper on that, saying, is that irrelevant now? Because the point is, are we going the dinosaur way? Because if you look at any of these are the Earth system functions. Like if you look at the carbon dioxide, it is going up this way. Nitrous oxide this way. Methane, stratospheric, ozone. If you look at surface temperature, ocean acidification, marine fish capture, shrimp aquaculture. If you look at all of these things, optimal forest loss, they're all increasing at an exponential rate. I mean, obviously as engineers we know that one goes like this. You all have studied basics of control systems, right? If you look at any system that is going like this, exponential thing, the poles are in the right half plane, right? The system is going to crash. Right? Is that not what is very apparent from all of this? That is why I have said, is it that we are going the dinosaur way? Because we don't know whether it is going to come down, and we are having tipped the system, and it's a complex system. And if you study the nonlinear dynamics, you know that this was about 5 years ago, and this is today, last year's graph. Already some of these other things have exceeded. If you look at the difference between this, and if you look at, for example, the phosphorus cycle, for example, look at the phosphorus cycle here. It was just barely going to, green is the safe zone. Anything outside that is not safe. So you see that in the next one? You see that it's out. Yeah, there, you see? Phosphorus has exceeded. This is in the last 7, 8 years. So we have exceeded a lot of the planetary boundaries in many of these things. And many of, in fact, recently green water has also increased. Green water is the water very important for our agriculture. And I know many of you might be in the NHPC also managing multi-purpose projects where you have to regulate the dams. That's a very interesting problem because do you prioritize irrigation or power generation? So this is where the kind of concept of resilience comes in. So what is resilience? There are many, many definitions of resilience. So people say it is a capacity to persist in face of change, to continue to develop with ever-changing environments. Resilience is the capacity of the system to withstand shocks, so things of that. But what is then resilience thinking? It is the idea of how do you manage periods of gradual change with rapid change and how do you adapt for it, how do you face that? And then what is this resilience and resilience thinking and anything in the scientific literature? If you think about it, it came from ecological research by Collins. What he looked at was, you have the phase diagram, right? So when you look at the phase diagrams in a complex system, you can have stable points basically. These are essentially the steady states of our system. You can have in a complex system, you can have multiple steady states. So what they are talking about is stability domains or basins of attraction, which means they are essentially, if you think about it, think of like a hilly area with hills and valleys. Those valleys are basins of attraction. If you put a ball on any of those hills, it will come down to the valley, right? You can have multiple such hills where water or ball will go down to those valleys. Those are essentially your basins of attraction. There are things like that. Those are stable ecosystem, stable points for ecosystem. Collins talked about it, especially in the context of fishing and all those things. And that led to how do we manage in an adaptive way? Because climate change is a reality, and then this is driver of what is called as a socio-ecological systems research in a big way. And this is essentially from that discussion, we can think about how resilience is about adaptability, it is about transformability, Basically, if I have to say in a common language, it is planning to not have a plan. How do you basically confront situations where you have like unexpected this thing and you don't know what that thing is. Then the question is, again, resilience of what, for whom, and for what, of what? Resilience of what, for what, and for whom? And the thing is, sometimes this is the actions that are aimed at interventions, resilience and challenge sustainability. So I hope you look at that, what that is saying. It's very important to look at the whole system because many of you, that's why I was referring to how you will have to confront these problems, because when you go into leadership positions 10 years down the line, 15 years down the line, you will be confronted with these kind of things. Is an individual action better, or how should I devise a policy that is actually doing global good and not just focused on individual good? So some terminologies, because we need to make sure that as engineers, terminologies, things are perfect. So what does sustainability come from? It comes from some means that is below and tenure means to hold, something that holds from the bottom, supports. That is essentially what sustainability is. And then stability means, again, it's a kind of control systems understanding, to stand firm or steady. So if there is some disturbance, it just stays there. And then robustness means strong. If there is a disturbance that is trying to push, it does not move, it stays there. That's essentially your robustness. What is resilience? Imagine like a steel bar versus a bar that is made of, let's say, rubber, right? Steel bar, if you try to push it, it will not bend. That is robust. Or a glass bar will be robust, but then it is brittle. It is not resilient, because if you push it too far, it will break. Whereas a rubber bar, it will go back and come back to the original state. That is essentially the kind of rebounding effect, that is the resilience. Also the common word, the way that we use resilience is also conveys that meaning. Vulnerability is, of course, the propensity for injury and then how vulnerable it is. Fragility is to break. Vulnerable is for small damage, whereas fragility is for the total system collapse. That's essentially what those things are. And if you think about it, this is essentially okay. So this one here that you see, the dotted line is a system with high stability because it is staying in that same form, whereas the one that is going out is essentially a system with low stability. Does that remind you of anything from your control theory? Stable in the sense of Lyapunov, system stability, that tube, right? Essentially, if a system can stay within the bounds, that's essentially what is a stable system. It can be applied not just to your electrical systems, but it can be applied to agricultural systems, it can be applied to ecosystems as well. So, robustness is, again, similarly think about it in that sense. Stability in the sense of Lyapunov, that is essentially your stable basin. If you think of that, the perturbation, a less robust system will have much bigger deviation from the stable point and then go and may not even end up there, like you see in that picture. And then here, when we talk about vulnerability, this is what the sensitivity is. If the system is exposed to this kind of a thing, then it can move. Adaptive capacity is ability to change so that that does not impact. And that one is, again, resilience, on the other hand, is the system has moved. Unlike that, the system actually has moved, but has recovered. You see, that is a more robust system. So, then the kind of thing is, are robustness and resilience the same thing? So, there are uncertainties in any complex system. The system boundaries matter, and of course, the feedbacks matter. And then the question becomes, how can we measure resilience? And when we talk about resilience, we have to think about different terms. And again, this is where it becomes very important when you are managing even your electrical systems. I'll give you an example of electrical systems later, but so please do think about these things. So the challenge in a shorter term is that resilience is essentially equal to the concept of robustness. So you can use the concepts of robustness and then see whether the system is resilient or not. Whereas in the intermediate term, it is about adaptability. and tolerance to school teachers. Whereas in the longer term, it is about transformability. How do you transform your system to a different state? And hidden fragilities and vulnerability, these are other concepts. A lot of it might be sounding like the control theory lecture where I'm talking about observability, controllability, things like that, but essentially a lot of things have come from there. So what is short term, what is long term really depends on the system characteristics. So this is something that I would like to put together to help explain that. So there are a few concepts that you want to really understand because this will be applicable even to your grid. Electricity grid, for example, would be governed by the same kind of principles as well. So if you think about it, let's say I have a system right there, okay? And then imagine that I'm pushing, basically these are three arrows, small arrows, and the size of arrow denotes the size of the distance, the perturbation. So let's say you have a system somewhere here, and then the perturbation one brings it to this point. And this zone that you see there is the stability basin. So essentially, by moving the system to some other set point, by perturbation 1, it basically goes back to the stable point again. So that system is robust to perturbation of type 1. Now let's say you also can have a perturbation type 2, which is a little larger than that. It could be going from steady state 1 to another state. Right? So system is stable for perturbation 1, but then it is not going out of the state. You see, these are the safe bounds. The box that you see is the safe bounds of operation with multiple points of stability. So it is going from this point again to another stable point, steady state 2. So it is robust to perturbation 2 as well. It is stable here, it is robust here. Now if you have perturbation 3, which is much bigger, then it is actually ending up in a different place. So that is a change system. That is like, I'm trying to break the system completely. It is not the same system anymore. It is a different system. Now what can happen is, just like how we exercise daily, right? What happens if we exercise daily? We are exercising with, let's say, 10 pounds, 20 pounds weight, and then 30 pound weight. Slowly muscle builds up. And after a few days, you see that even if you weigh, basically you're lifting 20 pounds weight, it doesn't feel that tiring, right? Because you have built enough mass. And then 30 pounds, you need to use that. So that essentially is like a small perturbation. That is like exercising. What that does is it could lead to two activities. If you have a system like a piece of glass, and I'm slowly hitting it, or if you take a piece of wire, how many of you have done this with a metal wire? Many people have done it, right? Hopefully. And what happens if you do it multiple times? It breaks. This is what is happening there. This essentially is what is happening. What is happening is these small perturbations are increasing the susceptibility of that system. So the stable basin of attraction, you see, this was much larger there. That it has become much smaller. Now, even if you perturb it with the same perturbation which was stable earlier, now the system actually goes back. It breaks. So it is like metal wire breaking after a few distance. Whereas if the system is anti-fragile, then these small things will actually strengthen it. It's like that exercise example that I gave. You see the stable system, that boundary has actually, basin of attraction has increased. Even with perturbation 2, now the system will stay there. It doesn't move, unlike here. See that? You're strengthening the system. So such systems are called anti-fragile systems. And the most of the systems that are designed by humans are not anti-fragile, they are fragile. And I will give you some examples of that. So, it actually requires thinking at the system design level when you are designing the systems so that we actually can make it anti-fragile. Most of the systems, on the other hand, which are natural, are by evolution, because of that, as a consequence of the evolution, they are anti-fragile. Of course, what I am saying is the disturbances have to be small. If I take the system and then put it to perturbation 3, it will break. So if I try to lift a 100 kg weight, my hand will break. That is there. But if I lift only 20 pounds, my muscle will be strengthened. Now, there is something called a law of conservation of fragility. So what is there essentially? If you have a system, complex system, there are outputs that are observable signals. You take measurements, and then you have some kind of a controller that makes the decision, and then you are feeding back the this is a classic control system thing, right? But then what you see here is this can be applied to how you make policies as well. So this is where we can think about how frequently should I change my policies? Should I be changing policies in response to changing needs every week, every month, every year, every 5 years? That is something that actually is something that we need to design as a system engineer. And that is where that resilience thing comes in. And basically all of these systems, essentially that frequency of estimates, classic control systems point of view. You can see the basically peak time, lag time, settling time, all those things. Yeah, so let me give you one example of how a farmer will respond to weather variations. So if it was something like this, farmer basically was trying to do and was trying to respond, what would a farmer try to do? A farmer would try to, let's say, I have some weather variations every other day. Today it rained, tomorrow it may or may not rain. So what would I do? I would try to change the irrigation practice. So whether I'm watering or not, I will try to change it. So that is an immediate short-term response. That is the robustness equal to resilience. But now let's say I see this happening over all the year, 1 year. What will I do? I'll try to change the irrigation system and try to make it more efficient. So that I can plan my irrigation system better, so that maybe I'll change the flood irrigation with a drip irrigation system, so that water use is more efficient. I can conserve the water and use it better. Whereas, if the drought persists for 2 years, 3 years, 4 years, then what will I do? I'll probably change the crop, right? That is the adaptation. And what happens if that persists even further? I may not even do farming at all. I may shift from a regular crop like paddy or wheat to something like a grassland, because water is not sufficient. That is evolvability of the system. So that is what essentially you are seeing here. What you are seeing is, yes, you can have the desired output, and then if you respond too frequently, you can have this kind of increased disturbance frequencies and this kind of a chip in the noise and then output. And these will impact what kind of decision you are going to make. And this essentially is also something that is used very much in the irrigation planning. Why am I talking about irrigation planning? Because that will determine how much water your catchment area will require from any hydropower project, for example. And then this adaptation and transformation and resilience, so we need to quantify that too. And then what does the short term and intermediate and long term time scales mean? What is the significance of these multiple time scales? What are the spatio-temporal dynamics in regulatory systems? Is something that you need to think about. So if you have a system, these are the kind of things that you will have to design for. So you can have a system where it could be pushed to this side. So then at an unknown time, you need to anticipate an event. This is an inner spiral. Try to monitor, respond, recover, learn, and then have a self-monitoring system. If it moves out, you try to again come back to the center. And how you do it is through all of these things, by putting in system to anticipate basically your perturbations, monitor them actively, when that happens, respond, and then try to recover, and then learn. This is the same thing that you can actually apply to disaster management. So think about what will happen to your electricity grid if there is a cyclone moving. You can actually use this kind of a model to think about that and put in robust plans so that you cannot avoid obviously the cyclones coming to an area, but you can actually respond and reduce the response time. What happens if there is a electricity grid shutdown in some place, or will that lead to national grid shutdown? These are all the things that you can think about. And so, now there are different frameworks. I'm just going to breeze through them just so that you can get an idea about what is it that I'm talking about. But you can have referred to papers in every place, so you can, if you are interested, you can go there. But there are qualitative and quantitative metrics. Qualitative assessments are typically used in the socio-ecological systems where they try to understand much more about qualitative frameworks. Identify the appropriate scale of the system, internal and external drivers, key players, conceptual models for activities. These are the kinds of things that you would probably use if you are doing a field survey and trying to come up with policies where people are involved. Same thing with the other things where we can either look into 3 dimensions where you look at the buffer capacity, the self-organization capacity, and the ability to adapt. This is where local governments, all of those things come into play. And buffer capacity and self-organization, this is something that you can use very well for your disaster planning as well. So similarly, there are many things like this. So I'm not getting to all of them. And another qualitative framework is to describe the system, identify the system dynamics, find out what are the interactions that are taking place, and then what is the system governance, what are the key factors in which that the system actually works, and then act on that assessment, and then keep repeating that. Now, if you want to do that in a quantitative way, because we would like to quantify things, so this is one kind of a metric where you actually can use how the system has recovered. What this could be, the y-axis could be anything that would define the system performance, and this is the time. So you see that as the resilience loss, essentially, and then try to do this, because if it happens too many times, if it is a fragile system, it will break, and that's why there is that integration with time. Then this is another thing where you actually are looking at the area under basically the curve there to look at the time that is needed to recover. And then you are kind of coming up with some kind of an average there and quantifying that. And this is again another one very commonly used in economic resilience, because if there is a loss of income, trying to come back to that kind of a performance is this thing. And it may not always reach. Essentially, it is nothing but a P control. Right? If you have a proportional control, you never reach to a steady state, right? It is always some level, something of that sort. And then this is another one where you actually look at the system performance in time. So that is essentially how you are doing. So this is called, because you are looking at it in terms of time, we call it as a dynamic resilience. And you also look at various things here. You can, from the disruptive event, you can look at, first of all, before the disruptive event, you look at reliability. So if I have a power system, I'm looking at the reliability of a power plant. If there's some kind of a disruptive event, I look at the vulnerability for that. And if something happens there, I want to look at the recoverability of that state. There are things like local resilience, global resilience. These things will apply for a region and a national network and a global network, for example. These are some kind of assessment frameworks. Yes, I want to talk about a few examples now. So, about cell responses, how many of you have taken biology? No? Yes, okay, one. So maybe I'll skip that example. I'll go directly to the variations in scales across systems, then optimization versus redundancy. This is something that we will all understand. What is the driver when we talk about any system, engineering system? What is it that we want to do? We want to optimize the performance, right? We always want to optimize it for energy, total economic cost. This is what we are drilled into. But that is totally antithetical to the concept of resilience. And because, see, if you think about it, Nasser Nicholas Taleb, he was the author of that Black Swan and Anti-Fragile, very good risk analysis professor. One of the things he says is, if economists had their way, we would only have one lung. Those two lungs are redundant, right? One kidney. Because why do we need two kidneys? One kidney is enough. So if you think about it, it's essential, because even if we lose one, we have that redundancy, and these are mission critical components. So when you study reliability engineering, you get that thing there, right? I mean, if you have a mission critical component, you want to have a standby. This is something similar to that as well here. So when we talk about optimization, whenever you have something on a standby, there's some capital cost. You're essentially putting cost there, and it's not getting the utilization time for that would be very small fraction. So that kind of a redundancy is totally against the concept of optimization. But we need to, as engineers, we need to balance these two requirements. So I'll let that sink in a little bit. When we talk about ecological and socio-economic systems, there are many systems across the world, like financial systems, which we have designed as human beings, because it has evolved through human interactions. Similarly with the energy systems and the food systems. They are essentially what we call as very fragile systems. What is a system? Essentially, it is something that will have a source, link, inflows, stocks, outflows, some kind of a feedback, and some kind of a measurement and feedback and control. Now, when we talk about systems, they are not built in vacuum. There are some things called archetypes. System archetypes, yes. So this is an archetype that is very, very commonly used and found in a lot of systems. What is called as the limits to growth. What this basically archetype is telling you is, no matter how much you push the system, there is a maximum amount of growth that can happen there. So this is because of some kind of a negative reinforcing loop that happens there in terms of the performance. You see this negative performance loop? That actually enhances the limiting action, which reduces the performance. So there is always a limit to what it can achieve. So this is the limits to growth. This is exactly what humanity is facing today, because we are a resource constrained planet. Because you don't have infinite supply of lithium, you don't have infinite supply of fresh water. So if you want to build a thermal power plant, you need to worry about where you get the water for cooling. So, I mean, if you think about same thing about nuclear energy as well, you don't have infinite supply of uranium. These are all things that actually can limit the growth. Then there is another archetype called fixes that fail. This is a very common example you will all be familiar with. Just before the election time, somebody will come and then try to patch up the road, all the potholes. And they will do their patchwork, and after it rains, it goes away. And these are the fixes that are temporary fixes that actually increase the problem symptom and goes, and then there are these unintended consequences, and that reinforces the problem. The potholes become bigger and bigger, and actually the whole road actually goes back. This is something called a fixes that fail. So we have to be very careful when we design the policies and look at any strategies that those fixes don't cause more problems. And this requires subtle thinking to understand how is the system behaving. And another one that is very common is the tragedy of the commons. Yeah, tragedy of the commons is essentially like that story, right? Have you heard of the story where the king was there, and then he said, people in my kingdom are all honest. So, and he said, I will show you. Then I said, okay, show me. The mantri said, show me. Then he said, bring a glass of milk and pour it in that big bowl. So everybody poured, and then it was all full of milk and everything. So then the mantri said, okay, you did this in the day, now let's do that in the night. So then he said, you have to pour the milk in the night only. Come and pour your quota of 1 glass of milk. Next morning when they saw, it was full, but it was full of water. Because every fellow was thinking that other fellow will put milk, my glass of water does not matter. And what it ended up being was full of water only. So that is essentially the tragedy of commons. Whenever we talk about common resources like air, water, and pollution, these are all the tragedy of commons. The people will say, I'm polluting a small bit here. Doesn't matter. It matters. All of these things do matter. That is where we need to think about it. And there are ways to fix these kind of things. Each archetype, the failure that I'm describing, there are ways to counter that. For example, in the fixes that fail, you need to make sure that there will be short-term pain, but you need to go for the long-term this thing. And that is where your ability as manager will come into place, so that you can convince the audience that yes, this is something that we need to do. Similarly, in the tragedy of commons as well, we need to take that long-term view and then do this. Yes. So now this comes back to what is a resilient system. So if you think about it, there are things called as core versus non-core goals. What is a system? When you think about it, it functions. It does have some core functions, and there are non-core elements of it. So for a system to be resilient, it is okay to leave the non-core goals. It is not okay to leave the core goals, because that will change the nature of the system. And you have to have that balance between the adaptiveness and the transformation. And then the emphasis will be on retaining those critical aspects which are essentially part of the core system. This is an example. I want to talk about synchronous effects and telecouplings. What does telecouplings mean? Seemingly unconnected systems, they can be connected by these linkages that you may not anticipate. Just to give you an example of the 2007, basically the financial crisis and things like that. So this is called essentially a slow process with basically long fuse big bang, and that means slowly go and then explode at one time. So you can have these things across multiple systems. So this is an example of that. Let me show you another picture. Yes, this is the picture that I wanted to get to. So this is what happened in the financial crisis. So what happened there was that there was this need to build the US economy. So there was a liberalization in the financial policies in 1995 onwards, 93, 95 onwards, Clinton era. And all that led to low interest rates. When you get money at low interest rates, it is not efficient to put it in the bank for savings because you'll get very low interest rate. What do people do? Immediately they try to put it in stocks so that you can try to get more returns. That was what was happening. When more money was flowing into the financial markets, immediately that was where do you trade? You will trade in commodities, right? You will get into things like energy. So there was a lot of that basically variation, that risk that flowed into energy systems. And as that went, what happened was also another regulation happened that was that you could use ethanol from what was a fuel oxidizer to as a fuel substitute. So before 2002, ethanol was used as a replacement for MTBE, methyl butyl ether, which was essentially like a anti-knock agent. So they were trying to use it as an oxidizer so that it reduces the temperature of the engine. Why do you need to reduce the temperature of the engine? Because you want to keep the combustion at lower temperatures so that your NOx emissions go down. So they wanted to control the NOx emissions. So they added MTBE earlier from 1977 onwards, because before that there was the smog issue in Los Angeles and a lot of the European and American cities. So they wanted to get rid of that. So they said, okay, we need to reduce the NOx. So let's put something as an additive agent. So that meant that they wanted to add MTBE. Why did they add MTBE? Because that was a molecule that GM could patent. And then in 2002 onwards, the ethanol production was increasing, and politically that was connected to some of the states in US like Iowa where the primary elections were being held. So those are electorally important. So the policy became that we will increase the market for ethanol because that was primarily being produced from corn. Now they said, okay, you can use the ethanol not just as a fuel replacement for MTBE, but you can use that as a fuel substitute as well. So instead of being 2% of petrol, legally it was increased to 10 to 15%. Now suddenly what happened to the ethanol market? It increased 4 or 5 times. And what was the consequence of that? There was a huge demand in the market, so a lot of the ethanol prices went up. As the ethanol prices went up, because now it was competing with petrol for the energy market, the corn prices went up, because that translates to the corn prices too, right? Because that is the feedstock. Now, as that happened, the variations in the financial market were transformed into energy market, because energy is traded on a daily basis, derivatives and all that. That came to food system markets, like the CBOT, the Chicago Board of Trade, where they trade the agricultural commodities. Earlier, it used to be seasonal variation. These markets were not very interesting to people. They were varying very slowly. But suddenly what happened was, because of this volatility in the financial markets transforming the energy system, impacted the food system. Suddenly you saw the corn prices going up and down. So suddenly, imagine what happens. I mean, now we are seeing the tomato prices, right? Tomato prices went from what, 20, 30 rupees to 150 rupees suddenly. It causes a lot of things. Tomatoes is just a vegetable. Imagine what will happen if that happens with the rice in India. India banned rice exports. Why do you think they did that? There is a lot of things going on geopolitically. We want to protect our thing first. Next year election be here. So you don't want volatility in price. All of these things come into picture. You have to think about all of these things when you are thinking from systems perspective. So you see, all of these things came in. What was the crisis? From the financial system, you had the US subprime crisis. And what was the consequence of the volatility in the energy system? Oil prices went up from $30, $40 a barrel to $147, $150 a barrel. What was the consequence of the food system? Food prices surged because US exports a lot of corn to many South American countries and African countries. So it is a stable food there. what was then, you would see, if you notice the press at that point, it was what was called as a food versus fuel debate. Why? Because food for people versus fuel for vehicles. Do I take the power and then use it as food, or do I convert it into fuel? What is this thing? Did somebody imagine in 1995 that liberalizing the interest rate or decreasing the interest rate would result in the food price surge 15 years down the line or lead to a housing crisis? This is what is called as a decoupling. This is something that we need to be aware of, and this is also something called as synchronous effects, because they are all happening simultaneously, and this is what was last few slides, maybe that's an indication. Go back, please. Go back one slide. This is what I was talking about. That you can have these kind of variations that transcend the systemic boundaries from one system to the other system, and then cause a global crisis at a system level. Why is this important? Imagine what happened to the US. I think one of the electrical grid system, their electrical grid system in 2002, I think. There was a tree. There was some kind of a thunderstorm passing through the Washington state in the Pacific Northwest. A tree fell on a transformer, the power line. Transformer blew up. Because of their systems, that entire part of that grid went down. And then that cascaded down, and entire western half of the US was in some kind of a blackout. Same thing happened around 2003 in New York as well. There was a blackout around August 15 time frame. Remember that because I landed there. And these are the kind of things that can happen. So this is not some kind of a theoretical problem I'm talking about. This is something that you need to build the resilience into your systems. In India, we have a lot of disasters, natural disasters that happen. We need to make sure that our systems are resilient. And especially if you have a lot of people interactions, and when people are involved, we need to prepare for that and think of immediate robustness, adaptability, so that robustness is so that you can withstand. Adaptability is, if the crisis comes, how do you adapt it and bring it back, and then transform if needed, and finally evolve into a better system. And all of these things are part of what is called as resilience. Next and next. Yes. So this is something, again, that I wanted to talk about in your context. I'll try to give an example. I'm not an expert on any of these things. I have done some work on the solar and basically looking at its impact, the telecouplings. Let me give you a small story. So you're all familiar with the decent solar photovoltaic part, right? We have two kind of programs. One is large grid systems, which are like mega projects, 2,000 megawatts, 5,000 megawatts, or things like that, big ones, farms, solar farms. And then also the household rooftop type solar systems. And also one of the things that government wanted to encourage was a lot of electricity was being used by farmers for pumping the water, right? And then so they wanted to provide free power. That's very common. So now they wanted to say, okay, now we have new photovoltaic systems. Let us put a small system there and put a water pump that basically can pump the groundwater. Now, there were policies across many states where these systems were heavily subsidized. Now, what did that do? If I have to pay for power, what would that mean? I will actually use it very carefully. Now, if it was a grid controlled power, even if it was free power, what would that mean? I can time it when I want to give the power. So it doesn't have to be during the peak load times during the day, it can be during the night. And in fact, you would see a lot of farmers report, newspaper reports, farmer dying of a snake bite or current shock at 3 a.m. He was there in the farm at 3 a.m. to switch on the pump. Why? Because power was being given there. So you can increase the system efficiency, right? What happened then was also then, now suddenly what happens when I have a solar photovoltaic panel and a pump, water pump that will run on sun? It is free. I have put some capital, maybe 10% or 20% of the system cost. Rest of that was given by the government. Now I have a system. I don't need to turn off. Is there an incentive to turn it off? No incentive. I'll just pump water. What happens to my water use efficiency? Goes down. And what happens if many people practice this tragedy of commons? What happens to the groundwater levels? it goes down. If I'm in a water-stressed region like northern Karnataka, what would be the impact of that? Groundwater depletion. What were we trying to do? We are trying to promote grid independence. What did we end up with? Groundwater depletion. Now imagine the same thing in Bihar. There it is not a problem. Why? Because the groundwater levels are much higher. So what should then, this is where that kind of thinking should come, policy thinking. What did this was tried, and then the policymakers also came up with solutions to their credit. It's not that we were only talking about problems here. What did they come up with? Then they said, okay, we should not give incentives equally everywhere. We should support the farmers everywhere, but not give them equal incentives. What did we do? In Bihar and many of the eastern Uttar Pradesh regions where the farmers are capital poor, we give them support and then have them buy the system and then let them operate. Even if they pump it all day, there is no problem. And then in northern Karnataka, we don't do that. We actually have them pay a little bit more and buy back the electricity from them. And what will that do? That fellow is going to sell it at a higher price than what he is paying. So there is an incentive to generate more electricity. So they will naturally optimize it for more electricity production. Therefore, that optimization can naturally happen in the field. So this is something that people would like. And just to give you that kind of a connections, unintended consequences. Now think about what will happen when you are trying to move to large-scale renewable power sources. You already know that when we are trying to replace higher and higher fractions of energy in the grid. In India right now it is not a problem, but because we are essentially a power deficit country, any power that we get is good for us now. But what will happen 20 years down the line? Remember I was telling you all that I'm here to talk about problems that you may face 20 years so that to provide tools for you to think further. What will happen 20 years down the line? Will be far surplus in capacity. Then you will be ending up in the same problems in Netherlands and some of the European countries are ending up with. So then you will have to think about how do I optimize how I'm using my large hydropower, coal, small hydropower, wind, all of these systems. And you also have to think about how do I make sure that the system is resilient so that there are no catastrophic shutdowns. Too much of optimization may not be a good thing too. Some redundancy would be required. So these are some of the things you need to think. Of course, in terms of storage, what would be a good thing? Hydro is something that is well known. Batteries. We are talking about these huge mega batteries, Tesla batteries, right? 1 megawatt hour kind of setups that they put. You can also think about these electric vehicles as a distributed source of power, right? That they can actually store. So you could think of these basically car parking areas where you go in the morning, plug in your car, and essentially it will charge during the day, and then or things like that, and distributed kind of storage. Again, thinking about base load, peak load versus on-demand power, these are all considerations if you want to really design a system that is resilient. So, what are the tools that you need to think about resilience when we talk about resilience thinking? There are 7 tools. Again, it's not my thing that I have come up with. There's something that the Stockholm Resilience Center has come up with, and you can find it here on Anthropocene website. So there are 7 things. First thing is you really want to maintain some kind of redundancy and some kind of diversity. So having a mix of various power sources which will have different modes of failure will increase the diversity of your grid and also increase the redundancy. Trying to manage the slow variables and the feedbacks. What do I mean by that? Some things change very slowly and we don't get to notice that. We need to be very aware of what is happening and the kind of feedbacks that we get. So that is something that we need to really think about. Foster complex adaptive systems. So systems that are naturally evolved and also something that are adaptive is something that we need to think about and see how we can strengthen them. Manage connectivity. Too much connectivity is not always good. Sometimes you will have to think about what kind of, how do you manage the connectivity in such a way that resilience and optimized performance is there. Always decentralize. Decentralization is a key for resilience. Again, you have to balance that with the economics also. And encourage learning, of course, where people are good. And then broaden the participation. Again, this kind of decentralized thinking really helps. These are 7 things of resilience thinking. And then, I'm not here only to say that, okay, we are in a resource-constrained world, it's all doom and gloom. No, things are actually improved. If you look at hunger, children dying, oil spills, solar panel prices, child labor, deaths from disasters, things have been going down, things are improving. And there are other things like electricity coverage, harvest, expensive solar panels, child cancer survival, girls in school, nature that is protected. All of these things, there are things that are improving. Some bad things are reducing, good things are improving in the world. So this is where we need to kind of check our biases. There is a wonderful book I would recommend you all to read. It is called Factfulness by Professor Hans Rosling. Very good this thing that actually talks about what are the common things that we miss. Not because we are actually biased or anything, but because we fail to see that. Because if you look at any news coverage, so it will be either on this extreme or that extreme. Whereas the vast majority will be in the medium, will be somewhere there. And always expect bad news in the newspaper. Good news is not TRP increasing. And then things are often projected to be linear. They don't go, nothing goes like that. They will bend, they will stabilize. Risks need to be calculated. And then always compare. Because this is something that people use, right? They will say 2 lakh people died in India because of some disease. Now, of course, we have 1.4 billion people. You need to look at it per capita also. I mean, important. And also, don't generalize too much because there are variations. We need to be comparing apples to oranges. So we shouldn't be comparing. And static changes, there are changes that are very slow. But things do improve over a long time, and we need to be thinking about it. And have multiple toolboxes. This is something that I tell my students also, and I would tell you also, have multiple tools. What does multiple tools mean? Many perspectives to look at the same problem. So that is very important. And then, rather than blaming things, there is actually better to look at it very objectively, and small steps of improvement actually can help. So putting it all together, when you think about any system, you need to consider multiple factors. I talked about resilience thinking, but as engineers, we need to look at technical feasibility first, resource sustainability. We need to do techno-economic analysis because we just cannot do analysis and stay there. We have to come up with solutions that are economically viable. We need to look into the environmental impacts, social and policy aspects, and risk assessment. These are all the multiple dimensions that you will be expected to address and come up with policies and manage your systems as you move forward in your careers. So, with that, I would like to wish you the very best in your careers as you move forward. Thank you so much.
Queries? I can ask queries. Don't hesitate to ask the questions.
Sorry about that. If you have any questions, I'll be more than happy to talk. Sorry. You're all two boards I just came now.
Or any of your opinion in this subject, that is also you can.
How many of you have heard about resilience and resilience thinking just before this talk?
Resilience in physics.
Physics, yes. How many of you have taken some control systems courses?
Almost all of them are engineers.
Basically, engineers, right?
Yes.
Electrical engineering background and all that?
And mechanical.
Mechanical also control is a
Robotics.
part. More control. Or something you want to add or somebody? Yes, please. Mike, did it.
Start in the finance, it will go to energy and then food. So
It went that way.
Coupled.
Huh.
And we are thinking resilience will solve this issue. But instead of resilience, because there is some resilience loss, even resilience will happen, we should think decoupling of this all sector by creating some code in that sector.
Yes.
That will be better, even no loss will happen in other sector.
Exactly. What do you think our government is doing with the FCI godowns? Food stocking to prevent that shocks. How do we do that for energy? Maybe what is that? That is what essentially is the strategic reserves. What do we do with the economic system? I don't know. I don't know really on that. So I think, but we need to be thinking. So there are ways to increase redundancies. Actually, that is what we are doing, right? If I'm going to balance my input to output, demand to the supply, and on a day-to-day basis, then what will happen if my ship is 2 days late? So you need to think about it at a systems level. Then things can improve. I'm not saying that was done then. I'm not saying that it is already done. It's a work in progress that we need to think about it because this is not in one person's hands. That is the thing. It's a global system. We need to at least manage our own regions. I don't know whether that answers your question, but we need to think about building redundancies into our systems at all levels. Thank you. Thank you.
Thank you so much, sir, for such an informative session. Our Director General, Dr. Tripta Thakur, has also joined us. I request ma'am to please address the seminar.
Please address the seminar. Yes, address everything.
So, moving forward, I request our Director General to please felicitate our keynote speaker with a memento and shawl.
इधर ही आ जा, इधर ही आ जा प्लीज.
Thank you so much, ma'am. I now request your Principal Director, Dr. Manju ma'am, to please give her a vote of thanks.
Yes, please. बहुत busy है ना? आप भी तो
Respected Professor Suryanaraya Murthy, National Coordinator, Indian Knowledge Systems, AICTE-Ministry of Education, Government of India, and Professor IIT Indore, Dr. Tripta Thakur, Director General NPTI, Dr. NP Srivastava, Director Projects, Sri N.R. Haridas, Director Training, Sri D.S. Sahu, Director Simulator, all the officers and staff members, participants, ladies and gentlemen, it's an honor for me to propose a vote of thanks on this occasion. I take this opportunity to thank Professor Suryanaraya for sparing his valuable time and coming all the way to NPTI for addressing the participants on a very important topic of resilience, thinking for managing our resource-constrained world. We are grateful to you, sir. Sir, thank you so much for coming all the way and talking about such an interesting topic, and the way you have explained that was so wonderful, giving a different perspective. Thank you so much, sir. We are grateful to our Director General, Dr. Tripta Thakur. Because of her, we got to, got an opportunity to listen to you, sir. Thank you so much, ma'am, for giving us an opportunity to, inviting sir for this topic. Thank you. And thankful to all the participants who have very, participated in this session, and all of them have listened to you very, with kind of silence, and they had some questions also. I am sure that they have a different perspective also, which later on maybe they'll share with you when we are out in the for the team. I want to thank Dr. NP Srivastava and Dr. Vatsila Sharma, who are the coordinators for Mission Live, and for arranging and organizing this seminar. Thank you so much, Dr. Srivastava. I also want to thank all the media team, all the IT and other, all the people who are involved in making this seminar a great success. Thank you all. Thank you.
I don't know whether it connected.